So let me introduce you. There are a number of colleagues here at the University of Engineering and Technology and research students. And we have colleagues around in Vietnam too. Some are in the US, in Sweden, are also online with us. So you have seen this invitation that we broadcast around. So I would not read this again, but Professor Merouane is very well-known internationally in the field of ICT. He has so many prizes, okay, especially in field for papers and technology. So that he's very experienced in both research and development. He's what I would like to let you know that you might, because you may not know Professor Merouane. In the past, he's a close friend of us here in Vietnam. This is in 2008. It's the first time we organized what is called now the Advanced Technologies for Communications Conference, ATC. That's the first ATC. And he was with us from the start, giving us a tutorial on mobile flexible network there. That was 2018, 2008. And 2009 he came back and he was giving a keynote speech in physical layer security. Some students are working on that now in our lab. 2010, he also came and gave another talk. This time it's on green communication. So he actually has been with us for many years. He also gave classes for the master program. I think we have Mai. Mai is here, Merouane.
Oh, hi, Mai.
Mai was in the class of that master program. And there's another one in Vietnam that is important for the field of communication, is the journal on electronics and communications. Okay, and if you can see that, actually the very first volume, very first number, and the first paper is the one that Merouane gave this an article on theoretical foundations of mobile flexible networks, and even the picture, the front page, the cover of the journal is the picture from the paper. Okay. That was back then, and then in 2014, Merouane, 14, yeah, Merouane, 13, Merouane, he joined Huawei and creating this R&D research center, Huawei funds. And when we started our institute here, AVITECH, and I was pleased to invite him to join us as an advisor on board. Here we have also Professor Bing, we have a few other people, Professor Đỗ Ngọc Minh. So Merouane has always given me lots of inspirations for development of the field for myself, and also for what I've been trying to do in Vietnam. So he's been very busy, so it's been difficult lately to invite him to come over to Vietnam. But luckily, somehow, with this COVID, people start, like giving seminars online. So this is a great honor and pleasure to invite you again, Merouane, to give talk to us here in Vietnam. And the reason for this talk is that we would like to look into frontier research type of thing in Vietnam, trying to see how we can develop things that are that have wide impact, sort of breakthrough. It is difficult, of course. So we would like to hear the experience from great researchers and great people who have experience with both research, theoretical research, and also technological research. And Merouane has recently given a talk on this, and here is the one of the slides that I had. So here you can see that it's between innovation 1.0 and innovation 2.0. What is this? And it's very exciting. And and with that, I would like to hand over to Merouane to give us a talk on this from innovation to invention. Thank you, Merouane.
Yeah, thanks very much. So I don't know if you see my slides or I have to get back the hand. Hello?
Can you?
Okay. I think I can share. Okay, I see. I can share. Good. I hope so. Okay. You see my slides, Trong?
Yes. Can you blow it up to full screen?
Is it okay? You see full screen?
Okay. Thank you.
Okay, good. Okay, so first of all, I'm very happy to have the opportunity to speak with you. As Trong mentioned already, I am very, let's say, connected to many of the Vietnamese researchers. Of course, Trong is somebody I've been meeting and knowing since many years. In fact, already more than 20 years, even we're going into 25 years now. And basically, I had the opportunity to come many times, giving courses in master programs, especially as at the time, Supélec had some joint research agreements with some of the different, I would say, master programs that were taking place in Vietnam. And I had the opportunity to teach there and see also the breadth of excellence of students that were there. I had also the opportunity to welcome some of the students to work with me. And also we had a lot of research ongoing between, I would say, the French community and also the Vietnamese community. So of course, as Trong said, lately I didn't have the opportunity to come back. I hope this talk will be the starting point of many new, I would say, collaborations that we could start together on the different research topics that I'll be mentioning today. My talk is going to be about a more general talk. Of course, I can, on any kind of request, give you more information after my talk, and you can send me an email. That's the first thing. And of course, depending on your interest, Trong can summarize those interests, and I can give more or less a specific talk on a given theme, and which will be more technical. So today, the opportunity that I'm giving here to you is to provide you an overview of what I think is the most important things that are going to be happening in the ICT field. But on a more technical aspects, you can of course contact me and I'll give you more information or give a specific talk on one of these aspects. So as far as I'm concerned, I'm a researcher and I've been working since 20 years, and I would say in the telecom industry, with a more or less background on mathematics and physics, because that's my background, and I've been basically more looking at the fundamental aspects of ICT in the general meaning. I'm also, I would say, since 10 years, more or less what we call a serial creator of labs, in the sense that I've put into place a chair at Supelec. And then I've been putting into place, I think, two successful labs. One called the Huawei Mathematical and Algorithm Sciences Lab in Paris, which has roughly today more than 100 people who have worked basically the 5G of the company, and now also is working on the 6G aspects of the company. And 1 year ago, I also established another lab more on the fundamental aspects of mathematics and data science, more focused on computing, which is also, I think, very important. And it's called the Lagrange Mathematical and Computing Center. And of course, I'm involved, like many of you, in the IEEE community, different, I would say, scientific community, working more or less on two major application fields, which are 5G and beyond, and AI, which is also getting hype. So before starting, I would like to give you an overview of what's happening in industry. And I'm going to take an example, which I know very well, which is the example of Huawei, and which showcases also the major changes which you are also encountering within the university in terms of the blurring aspects between what we call the engineering department and the computer science department. And this is what I call here the convergence. The convergence of communication and computing is putting back all the cards in the sense that now the research that we were doing before is undergoing a big change. So Huawei started, as many of you know, 30 years ago as a CT company. CT company means communication technology company, providing the major infrastructure for the operators in the world. Infrastructure here means basically base stations, fiber, cables, all the things that operators basically sell. And as you can see, progressively, it went into what we call the device business. The device business here is meaning that you provide the screens where people see that information. So going from what I call here a connectivity, it became more basically into the device. And devices are, of course, smartphones, but also, of course, tablets, screens, things like that. And as you can see, recently, the progress has been much more focused on something related to the computing aspects. And computing here is more or less the capability to implement basically AI, and AI in a broad form, especially with its neural processing units, which are what we call more focused, I would say, deep learning algorithms. And today, a company which was a CT company is now more or less what we call an ICT company, information, communication, and technology. And the shift that we're seeing here, you're seeing it also in many other companies now in the world, where basically they are starting to look at what we call the end-to-end aspect. And the end-to-end aspect is very important because we previously had a very layered approach of how we design networks. And the layer approach came with all the OZ layers, and the cross layer tends to be at the heart of all the communication paradigms that we're doing today. And for that, basically, what needs to be done is more basically interdisciplinary research, in the sense that you need to talk more closely to the people who are doing hardware, to the people who are doing mathematics, to the people who are doing physics and chemistry in a way to understand basically the end-to-end performance of your system. This is also something that is happening, and I'm seeing it at the faculty and university. If you take the topic of AI today depends on your background. You can work on AI coming from a signal processing field. You can work on AI coming from a hardware field. You can come to AI coming from a computer science aspect, or you can come also to AI on more an electrical engineering aspect. And today you see that many of the top guns in AI are in general people who are having joint positions or even triple positions between CS department, electrical engineering department, and I would say the math department. And I think this is getting more and more in the ICT industry, where there's a blur in terms of the various departments, which are quite separate. And I think this is going to be also a game changer in the way teaching is being done at the different faculties in this, I would say, new phenomenon of topics that we're dealing with. Now, I have spent a lot of time working on various aspects that I'm showing here today. And I'm going to tell you two things that the industry has been working intensively on, and now a new aspect that the industry is willing to take the burden on. The first one is what I call business-driven research. So what is business-driven research? Well, business-driven research in general comes from problems that are posed by customers. Meaning that a company like us, in general, sells products, and the customer comes back with some requirements or changes to basically what was sold. In general, the time frame of business-driven research is of a 6 months to 18 months time frame. So basically, the problem is well defined. The degrees of freedom in terms of invention are quite limited. However, basically, you need to solve that problem. And in general, it's generally a problem of complexity or reduction of computational, I would say, resources. It's what I call here engineering research. Today, a large majority of companies do that. However, the kind of, I would say, added value that you can bring can be quite limited in the sense that basically you're not going to make a breakthrough, but you're going to solve an existing problem. As I told you, this kind of research for a company like Huawei is mostly like around 60% to 65%, basically, of the research which is ongoing in a company. And so typical problems are more or less, if you have a matrix, you need to invert it. We know that basically matrices in the classical form, the inversion complexity is of n cubed in terms of operation, and you're asked to reduce that complexity by exploiting some kind of structure that you can have in that matrix. That's called sparsity, and if it's sparse, then you can build up some algorithms which can do that. And in general, it's a problem of saying that I have an algorithm which runs within 5 milliseconds. Can you run it in 1 millisecond? More precisely, I give you another example. It's typically the example where you're asked that by a customer coming to you and telling you, look, I have basically a search algorithm today to do search in zip files. It's a bit complicated. What I mean by zip files is compressed files. So if you want to do search in compressed file, how you do today, well, you need to decompress the files, search basically inside, and then recompress. So this has two caveats. The first caveat is that when you do a search in a compressed file and you decompress it, it takes a lot of space within your servers. Second problem is that if you decide to decompress all the files to search the keyword within the files, then it takes a lot of time. So a customer would come to you and tell you, can you come up with an algorithm which can do a search directly on a compressed file? And then you have to put your researchers or your engineers on the problem to think, well, can I put some kind of header, okay, in the basically naming of the file so that immediately I can know that there's a big probability or not that basically the word is in that file. So I can reduce the search space and basically improve the efficiency of my search algorithm and reduce basically the time from basically 5 milliseconds to 1 millisecond. These are typical the typical problems that we face today when customers come, and it's mostly about basically optimization and engineering, and where basically you need very talented people who are able to understand at the same time the exact nature of the problem and solve it. You have to know that the majority of researchers prefer these kind of problems when they're well defined rather than when they're not well defined. And the reason is very easy, is that basically, in general, you can get quite rapidly recognition in these problems because it takes you 1 year, 18 months, and once you solve it, you can put it on your CV and get exactly recognition from the community and advanced. And we see it also, by the way, at universities today. If the problem is well defined, then it's quite immediate that you can get recognition from the management. When the problem is not well defined, then basically there's a big risk. And when there's a big risk, only few kind of researchers are willing to take the risk of that, and especially with the fact that the result can come only after a long time. So of course, this depends on the kind of management which is done in different universities and also in companies to be able to help people to do more risky research in terms of still getting a promotion when you did not get a result, but you were able to show that you did the right thing to solve it. So this comes back to my second type of research, which I call technology-driven research. And this is exactly what you have in the middle that you can call applied research. And here, basically, in a company like us, this is the time frame of research of something around 18 months to 7 years. It's mostly about building the portfolio of products of the company with technological programs that you build without a specific need from the market, but where you create the need. This is typically 5G. So 5G in our company started in 2010. In 2010, we had no clue what was 5G, but we built up the program for results to be in by 2017. And basically by that, we built a roadmap with each year, basically creating some milestones, and on which basically we believed that if it was successful, that the market would kick in. Today, we're doing the same thing for 6G, for information. We have built a research program which will last until 2027, such as 6G can kick in 2030. There is no market, there is no specific need, but we build up a research program and with a high risk of things not happening, which means also that in the type of research incentive that you do for your researchers, you need to be very careful in how you do it because you need to keep up the people working and motivated for 7 years with the risk of not having a result. So this also requires some kind of quite good management to be able to do that. And the last one, which is quite important, is what I call here vision-driven research. And vision-driven research here is mostly something that universities know how to do these things, which are mostly around making scientific breakthroughs. It's not technological breakthroughs, it's moving the boundaries of your research. And so here I'm going to explain to you why also a company like us has decided to invest in vision-driven research and why we're doing this today and why, by the way, many companies in the world are doing this today.
Merouane?
Okay, yeah?
The slides stay still, it's one slide of these 3 types of research, is that? No.
Yeah, it's still the same.
Oh, the same, okay, yeah. Okay, fine.
Yeah. And this is what I call here fundamental research. Now, to give you an example of the 3 things, let me give you a very specific example. If you take, for example, an engineering research, which is basically the diamond that you have here on the right, this could be seen as basically what we call 4G or LTE. Okay, LTE and 4G is based on the technology called OFDM. This is what I call here the engineering research. The applied research and how OFDM was made was thanks to people who have designed the algorithm behind the OFDM, which is called the FFT. This is the applied research. And what is the fundamental research behind is basically the Fourier transform. So it's thanks to some fundamental breakthrough called the Fourier transform that we were being able to develop after a couple of years the classical algorithm behind, which is called the FFT, and then basically being able to develop basically the technological, I would say, solution, which is called OFDM, which is at the heart of 4G. Another example, if you take basically the fundamental research, which is related to what we call the Galois field, number theory. Basically, this is a very specific example where Galois developed the whole framework of number theory. Okay? Then, of course, came in basically things which were on the binary field and for which we were able to build a whole binary framework. And this is the applied research. And for which then were invented codes which are related to turbo codes, LDPC codes, Polo codes. And so you can see that it takes a bit of time to make the transition. Same thing if you go back to the fundamental research related to harmonic analysis, okay, which dates back a long time ago. Then you have an applied research field which is called wavelets, and for which basically then you have some engineering research which is called JPEG 2000. JPEG 2000, for example, the standard is based on a breakthrough which was done in the applied research related to an algorithm called basically wavelets. And wavelets are based on harmonic analysis. So you can see here the division and how basically it can take time to progress towards these things. Now, to give you more specific example of this transition, and then I'll explain why fundamental research or invention or vision-driven is important, I'll give you, of course, the different aspects where you would fit in. If you look at what I call here the most business-driven research, well, this is mostly engineering optimization, and it's related, as you can see here, to 3G, 4G, cloud computing, heterogeneous computing, 3D cameras, for which basically it's mostly about solving existing problems and especially improvements of solutions which are there. And then you have what I call here the technological roadmap or technological driven research, which is happening today, which happened in the sense of building a research program, and you have it here through 5G, foldable screens, all optical network, SDN and FV. And today, as you can see, many companies have shifted more and more of their resources to take a leap in advance towards what I call here vision-driven research, which is more or less focused on technological invention and theoretical breakthrough. And here you can see the major topics which today are driving the majority of the ICT companies, which goes from terahertz, which is one of the frontier that we're seeing today in the wireless, to graphene-based CMOS, to quantum computing, to brain-computer interface, to bioelectronics, to photonics computing, to DNA data storage, to brain-like computing, and then to atomic scale manufacturing. And so the big question you can ask me is why today we're doing this transition. Well, the main reason is that many of the big fundamental breakthroughs were done 100 years ago. More precisely, they were done in 1948. 48 was a very big, important date in the sense that many of the fundamental papers were published that year. The fundamental paper of Shannon was published in 1948. The fundamental paper of Wiener, the father of signal processing, was published in 1948. The fundamental paper of game theory by von Neumann or Morgenstern was published in 1948. The von Neumann architecture of computers was published in 1948. Roughly, the fundamental paper of Alan Turing basically was nearly published in 1948. It was published a couple of years later, but basically the draft was done in 1948. Of course, there's a reason why things came in 1948. It was mostly about unclassifying some documents, which were done during World War II. But here what I'm saying is that the majority, and we'll see, of the breakthroughs were done 100 years ago, and since then we've been doing the engineering and optimization of the concepts which were built there. And today, unfortunately, we're seeing that within the next couple of years, we'll be arriving to the limits of the engineering. The first limit is, of course, the Shannon law. Today, if you look at communication, we are nearly at the Shannon limit in many respects. And the question, of course, arises on how to go farther with that. And unfortunately, we don't know, especially if you take the case of fiber. Fiber is a nonlinear medium, and we have no clue on how to push the limit of fiber more, because basically we have no clue of how to compute what we call the nonlinear channel capacity, because everything has been done in the linear domain. Second thing which is also important is Moore's law. As you know, today the progress in AI is mostly a brute force, I would say, approach, meaning that the majority of gains are related to computing power. But that computing power has not been made due to a change of how computing is made, but just by adding more and more and more and more transistors in a given space, and for which we're also seeing basically the limits on how to go further. Same thing in terms of computing architectures. The majority of computing architectures today are built based on von Neumann architecture, where there's a clear separation between data and computing units. And where basically to compute, you move the data to the computing unit, and then basically you give the results. We know that this is extremely bad in the sense that you lose a lot of time just moving the data within a computing unit. And this is where there's a big loss of time. And you need basically to revisit how you do computing by doing some kind of in-memory computing. You need to bring closer, basically, the data near the computing unit. Why? Because we know that things are more data-centric today, and for which data is the heart. So you need to bring the computing towards the data and not data towards the computing. And basically, today, we know that if there's not a fundamental progress, which is made especially by you guys here at university, the whole ICT industry may collapse, in the sense that we will be doing more and more engineering optimization, but there's a limit to which we can do that engineering optimization. So we need to push those walls, the memory wall, the logic wall, the power wall, the thermal wall, and the interface wall. And if there's no big progress which is made, the whole industry may be at stake in terms of how we can go forward and how we can make breakthrough. And this goes back exactly to the point I mentioned, is that we see that due to, I think, a lack of risk that has been taken, especially by academia, today, all the fundamentals date back from a century. And so we need to revisit all these basic, I would say, results and see how to re-question not basically the papers, but re-question basically the hypothesis and basically the models which were put in those papers, so that we can basically regenerate a new breadth of breakthrough papers for which there's going to be one more 100 years of engineering research to build up on those papers. Again, those papers had nothing wrong. We'll talk about them. You need to read them. It's mostly about re-questioning the models, which obviously today do not hold anymore. So before I start giving you some insights on what I think are the possible directions on which you can invest your time, I'm going to go roughly, at least, on a couple of things which are happening in our industry, which I think are extremely important, and especially by the year 2030. So I have 6 or 7 slides, which showcases basically, from my point of view, the trends that we're seeing, and then we'll talk what will be the fundamental, I would say, routes to solve those problems. Of course, the first one is basically the fact that we are living what we call a fourth industrial revolution, with the fact that intelligence is highly embedded in nearly all the things that we're doing. And especially, as I told you, the ICT industry is changing towards what we call an intelligent world with three things. The first thing is the fact that all the things are connected. And this is the revolution related to the Internet of Things and the massive connectivity, which is bringing a breadth of new, I would say, challenges. Second is the fact that these things which are connected are empowered by a lot of computing resources, and which brings, of course, the possibility to have a pervasive AI, basically, world, in the sense that computing can be done up to the IoT. And so if you can do what we call on-device AI, or nearly basically computing at the edge of the network, you can imagine the whole complexity that you can create in a network. Of course, it brings a lot of good results in terms of privacy, but then you have also a lot of new algorithms that you need to develop, which are within the realm of federated learning, distributed AI. And the third one also, which is extremely important, is that radio waves have been used for many years to communicate data. And today we're seeing the fact that radio waves, and especially the fact that we can use now waves at more and more higher frequencies, can be used to sense. Sense in the sense that you use those waves to see your environment. And they can be used like radars, and this is typically what the industry is doing today in terms of using the radio waves to do fingerprinting, to scan, to be able to basically have a reflection by your electromagnetic wave, so that the reflection brings you a lot of information in terms of reconstructing your environment. This is, I think, going to be a big game changer, by the way, in 6G, where basically we know that a lot of the network that we're building for the future are for what we call intelligent robots, not for humans, and for which these robots need to use the electromagnetic waves to move within their surroundings and to see. And so those waves, we need to build up some good classification algorithms to be able to reconstruct the texture of your environment. And the people who work in electromagnetic waves know about that. This goes also to the fact that the network that we built until today, which was mostly based on IP protocol, has to be reconsidered in light of what I call here the Internet of Everything, in the sense that you start to have not anymore a PC internet, not anymore a mobile internet, not anymore what we're having today, an industrial internet, but more or less intelligent devices discussing with other intelligent devices, and for which all the problems of latency that we had before, all the problems of exchanges that we had before are totally different in the way we did with the classical IP type protocol, on which you always had a human at the back end of basically a terminal and another human at the back end of the terminal. Now, before I start on what I call here the scientific challenges, let me give you a rough idea of the major trends, which I think are going to be important by 2030. The first trend is, of course, what I call here hyper reality internet, in the sense that, as you all know, VR and AR is playing a more and more important role, especially in the gaming industry, and for which basically you need to be able to create some kind of immersive experience. What I mean here by immersive experience, meaning that you need to feel at a very long distance the same thing that is happening at that place. And for that, you need not to do some kind of teleportation, but you need to move in real time all the senses from one point to the other point. So this creates a lot of challenges in terms of extreme localization to create all that very good reconstruction of your environment, extremely good sensing and localization algorithm, but also bring all the senses with latency, which has to be also drastically reduced to what we have today in 5G, which is already a good thing when you think of the millisecond latency that we're talking about. Second is also the data rate, which is not sufficient today that we're having with 5G. And the reason is that the more you bring closer any kind of screen to your eye to be able to have this immersive experience, it creates a lot of granularity in terms of resolution. And so if you bring a screen which is at 1 meter from your eye, it's not the same thing as bringing, in terms of, let's say, high quality, a screen at 1 millimeter away from your eye. And we've been counting basically the data rate, which would be required to create that kind of immersive experience. We're talking about roughly 5 terabits per second. To give an example, today, 5G, in the best case, meaning in its peaky case, provides you around 20 gigabit per second. And so this is also a big challenge in terms of what are the KPIs, what I call here the key performance indicator that you need to build for basically 6G. The other in the same trend is basically this holographic experience, which is being built. And so here, why I decided to put this slide is basically because when we're talking about hologram, we're talking about optical. And this is also a big trend today that we're seeing, is basically the fact that many of the frameworks, many of the scientific breakthroughs which were done in the optical field are now being brought back to the people who are doing the RF things. Typically, we have to do what we call optical Fourier transforms. As you all know, today, when you try to do a Fourier transform, you do it in a digital manner to an FFT. But if you really want to do it fast, to be able to reconstruct some kind of a frequency environment, one way to do it is to do it in an optical way, and then basically to have some kind of reader which can read that. And there's a lot of work which is being done, and I think you need to spend a lot of time reading more and more the transactions on optics, which are also making some major breakthroughs, and for which we're bringing back a lot of optical algorithms to our discipline. The other, of course, aspect is also the fact that AI is also bringing a big game changer in basically the way we're constructing our network. So here there's two things. The first thing is basically using AI to improve your network. And this is the classical trend related to roughly automation, auto-optimization, and basically trying to bring some kind of end-performance improvements. The second thing for which people have not been working too much is basically building the network, such as you can do basically a better AI or pervasive AI computing, which is very distributed. This is what I call here network for AI, or AI for network. And basically, when you start doing a network for AI, the way you've been computing metrics is totally different. For example, today we know that when you start having an intelligent device talking to another intelligent device, well, basically you start building what we call a context in your communication. What I mean by context, in the classical model, you have memory and computing power, for which Shannon did not take into account. Well, basically, you can build up a model within your communication, and that model basically provides you a way to have an information which is sent, for which you require less bits to have the effective goal being done. This is typically something that happens to you with your wife or your husband. When you start talking many times, at one end, you don't need to tell again the whole story. You just need to give a couple of words and your partner understands everything. Why? Because you've been able to build a context in your communication This is called semantic communication. It's, of course, creating a new breadth of opportunities in the way we do research today. Now, the main reason why it was not taken before is that because in the classical model of Shannon, there was no memory. So every time you started the communication, you started it from scratch. You did not take into account the fact that there's a whole historical perspective that you did in your communication. And that's because you really reinitialize your communication every time you communicate. However, if you take into account that there's been a whole history of communication which has been done, you can exploit that context to do better communication. Same thing now on more I would say, the hardware. Of course, the big trend today is the fact that in terms of improvements of Moore's law, we have to move basically to more photonics. And this is what you're seeing today. And you're seeing, of course, a lot of photonics papers appearing. And that's basically because you need to go at the speed, not anymore of the electron, but the speed of light. And today, as I told you, a lot of processes that we were doing in a very digital manner can be done. Just think about the Fourier transform can be done in an optical manner, exactly because if you have a laser going through a cavity, then you know that basically you have a diffraction. And that diffraction is exactly the Fourier transform of that cavity. So if you have a cavity which is a square, then you get the classical, I would say, sinc function. If you have some kind of circle or cavity, then you have this Bessel function that you see, and you can construct very fast that Fourier transform much faster than an FFT would be doing it. Another thing also is the IP, and I told you about that. In the IP case, what I call the Internet Protocol, things have to change. And they have to change for a simple reason, is that you're not connecting people anymore, you're connecting machines. You're not connecting just 1 billion people, you're connecting billions of machines. You're connecting also things which are becoming smarter and which are security. And these things are also a big game changer in the way we're building things like that. Another also aspect, which is the big trend, is I told you the fact that today the majority of the AI trend is very cloudified. Cloudified meaning that everything, all the data has to go back in a central server to be computing. We know that this is not sustainable in terms of energy. It's not sustainable in terms of privacy. It's not sustainable also in terms of overloading the network. So you need basically to massively distribute your computing and find the right type of algorithm, which basically try to exchange not the data, but the models learned locally, and start federating those models to create some kind of meta model so that you can basically move forward. Last but not least, as I told you, is also the fact that the computer that we know has not changed. The computer is unfortunately the same as the one. We need to start thinking of non-von Neumann, and for which basically the whole idea of a central unit which computes a cache on which you're going to pour your data has to change, because you're losing a lot of time and doing some time of processing directly in the memory, okay? And this is the only way if we want to do a big progress around what we're doing. And the last one also, which I think also important, are by 2030, are the new trends that we're seeing, and especially the optical computing, which I think is going to be a big thing before the quantum computing aspects, and also before the brain-like computing. On the new material, you have to know I'm working intensively on that. The meta materials, which are quite important for the beyond massive MIMO realm, is also something extremely important to look at, in the sense that these materials have now properties which are providing you a way to change the environment in a very intelligent way. Let me now rapidly, for the time that I have, go roughly 2 aspects. I mean, I could spend hours, but at least 2 aspects which I think are very important. The first aspect is, of course, in communication, why I think there's still a lot of things to do there. I think today in communication, there's 4 paradigms that I'm putting here, which will be a game changer. The first paradigm is, okay, I don't know what happened. The first paradigm is basically the fact that uh, until now, to improve communication, people have been only trying to focus on the TX, the transmitter or receiver, to improve the communication link. We know today that if you want to improve, you need to change the environment, and which is something that I think all of you are aware of. However, it was quite hard to change the environment previously, in the sense that you needed to move the objects. We know today, thanks to what we call large intelligent surfaces, that there's a smart way to do that. Okay, and today you have a lot of work which is being done. I worked on that, for example, on meta materials, which basically change the texture of the environment to improve the capacity. Second thing, which I think is also important and a game changer is communication today, is the fact that memory is becoming more and more important. We have much more storage units, and storage is very cheap. And this is, of course, changing the way we do communication with semantic communication, distributed AI, multi-agent wireless system. The third one also, which I think is important, is related to the fact that physics is becoming extremely important in the way we do communication. We were not exploiting, basically, to its full length, the Maxwell equations, in the sense that we were solving the Maxwell equations by considering what we call exponentials. However, if you solve the Maxwell equations by taking new boundary conditions, you can showcase that you have new modes of transmissions. And instead of looking at massive MIMO, you will have systems considered as massive modes. And this is, for example, OEM, orbital angular momentum, Bessel beams, holographic MIMO, which is happening today. And the last one, which I think is a big thing today, is the fact that there's a lot of room of improvement in communication, even for problems which are as simple as PAPR, in the sense that we've been solving this problem mostly by compensating them. And why we compensate, in general, is because we don't know how to solve the problems when they become extremely complex and extremely nonlinear. And when you have nonlinear problems, as you all know, doing linearization is very bad. You need to solve the problem by considering the end-to-end model as a nonlinear problem, trying to solve that. And we're seeing already today some very good results of people trying to attack those problems. Now, in terms of specific scientific challenges, if you're working in the communication field, I have listed them here. And of course, I'd be willing, depending on your interest, to focus on one in the next presentation to give you a highlight, because each one takes at least like 1 hour of presentation. The first one is called electromagnetic information theory, which I think is the convergence of electromagnetics and information theory, which is getting important. The second one is, of course, the nonlinear signal processing theory, for which today we have some new kind of results which have been done, and there are some progress. The third one is multi-agent learning systems, in the sense that if you want to deal with the problem of distributed decisions, you need to build up a theory. The fourth one is signals for varying systems theory. Today, the majority of signals are based on linear invariant systems, and this is why typically OFDM is not good for highly time-varying channels, and for which basically today we have some new kind of trend called OTFS, others, which are trying to build those things. The fourth one I talked about was semantic communication theory. The other one is the theory of super resolution theory that I talked about, which is more or less a generalization of compressed sensing, and for which basically it has a very important impact on basically the problem of localization. The other one is how you start revisiting the problem of radars, and especially for sensing, where you have signals for integrated sensing and communication. The other one is the large-scale communication theory, which takes into account the massive connectivity and for which you need to revisit the way basically you build up information theory. The other one is the fact that you have short block length communication, and for which you need to build up something called non-equilibrium information theory. The other is the fact that, as you all know, you need to take into account traffic when you do communication. Today, the majority of people look at the full buffer case, meaning that you have, for some reason, always data to transmit, whereas we know that you need to take into account the fact that you have a traffic, to look at how you combine the basically buffer, scheduling, and your physical layer. The other one is the fact that things are heating. And so you need to build up energy efficient communication. This is what I call here thermodynamics of computation and communication. And the last one is what I call here non-coherent communication theory, in the sense that the majority of communication, for some reason which I can explain when I have time, try to come back to a scenario where you know the channel. Whereas we know that if you want to communicate, you need to find some kind of structure of your signal so that the channel does not destroy that structure and you can recover that. Of course, people have worked on blind methods in the 90s. We're going in that direction. But today we have some very new results related to how you can do what we call non-coherent codes, which have some very good structures and for which basically you don't need to do a training for that. The other two aspects I want to talk about is, of course, after communication, it's computing. And here again, we have some very important paradigms which are happening. The first one, as I told you about, is that you should not move anymore basically the data, because basically this is where you lose a lot of time. And this is what I call here in-memory processing intelligent. You have also to use more computing to move less data. And this is intelligent networks, in-network computing. You need also to use more computing to reduce latency and handle faults. This is called clone computing, coded computing. And the last one is basically to use more computing to automate chip design. And this is what we call the massive parallel combinatorial search and optimization. And here again, you have here a branch of new theory which are coming in, which I think are also going to have a big impact. And this goes from approximate computing theory. You don't need to have the results in exact manner because it costs you a lot. So an approximation can be as good as an exact result. In-memory processing theory, intelligent storage theory, intelligent networks theory, in-network computing theory, clone computing theory, coded computing theory, quantum algorithmic theory, Ising computation theory, spatial computing theory, non-von Neumann architectures theory, symbolic computing theory, and analog, which is coming back. And I told you why analog, at least in the optical way, is extremely important, computing theory. Again here, depending on your interest, I can next time spend 1 hour on one specific case and to show you the breadth of research which can be done at least on these things. So here what I tried to do on the last, I would say 4 slide, to showcase you 2 directions, one in communication and computing in terms of breakthrough research that needs to be done to move forward the boundaries of our things. And I think I'll stop here, and I'm willing to answer your questions, at least for this general introduction.
Thank you very much, Merouane.
I don't know if you heard me well, by the way.
Yeah, very good.
Okay.
For those online, you can just switch to the unmute your microphone and webcam to give questions to Merouane. It's open, I think.
The floor is open.
We have here Professor Bass, Vice President, UNU sitting next to me, and online as well also the Dr. from Wien University.
So sorry, Trung, maybe I didn't understand. I have a question from somebody. Is that what you're saying?
No, not yet. Not yet.
Oh, okay. Okay.
Okay. I can see that. So there, like we, as you explained, we sort of reached several important limits. Shannon, Moore, and linear in terms of signal processing linear theory, and we have to find out new theories that can help us reach the targeted applications in the future, like in 2030. Okay, however, like what you said is that those fundamental theory was back in almost 100 years. Now we are thinking, or we are starting new theory, and of course we don't know how long it's going to take. But what would you think about that? That's one first question that I'd like to ask. The second thing is that like doing breakthrough theory, apart from the passion, apart from like the hours, the efforts that we have to put in and wonder, there's a need for huge funding, investments. And we are from the two things here in Vietnam. One is we are a developing country, and the second thing is for us here is we're in a university. Okay, so what is sort of the interplay between university and big companies, and also the separation between or the interplay between developed country and developing countries, that to help us here sort of look into or develop like this kind of fundamental research. Yeah, thank you.
Those are good questions. So so the first question, I think, in the first one is very important. Is what I'm saying is that today we're still improving the system, but mostly by engineering, meaning that in the next 2 to 5 years, I think we'll be reaching basically the heating limits that we have by basically putting more and more devices on a single chip. And basically what I'm saying here is that if we want to meet the targets of 2030, there will not be any 6G if there's not, for example, a fundamental breakthrough in how we push the boundary of those fundamental papers. Now, how you do that, and I think I tried to show it, is very easy, is by re-questioning the assumptions which were made on those papers. Those papers were not wrong, of course, but by re-questioning the assumptions, this is how you basically improve. And this is the whole philosophy of research. In general, what you do is that you take off a hypothesis, and by reducing basically the assumption on that hypothesis, you can basically improve or generalize the results. So in the case, for example, in communication, which I know very well, the classical model of Shannon, which is basically you have a source, you have a channel, so you have a source encoder, you have a channel encoder, you have your AWN channel, and you have a decoder, is extremely good. But today it doesn't work like that, because basically in a transmission, you have memory here, you have memory here. So you can store basically your past communication. You don't delete everything, you have it. And then you have computing here, you have computing here, which means that once you communicate with somebody, you can create a context in your communication, and this changes the paradigm of how you do communicate, for example. And so you can transmit less bits to get a certain result, for example. And the same thing for the majority of models that we have today are not as simple as we had with the Wiener type. In this, because you go to millimeter wave communication, which is higher frequencies, you have more and more what we call amplifiers, which are not working in the linear regime. So when you're taking to the channel in general, you don't take into account the hardware discrepancies related to the fact that you're not operating in a nonlinear regime. And so the end-to-end channel, unfortunately, is some kind of a black box for which basically you need to solve the problem of a communication in a nonlinear medium due to the fact that the nonlinearities are brought basically by the hardware discrepancies that you have at the TX and RX. So you need to build up some kind of nonlinear signal processing. Today, you have some very good results which have been done related to Buzgong theorem, which tries to model these nonlinearities. And if you're not able to model those nonlinearities, today AI is able to solve you many of the problems which are nonlinear because you will start learning the black box. Of course, it's a brute force method. And basically, you're able to find what is the right input that you need to do in that thing. So what I'm saying here is that I think we will have some very interesting results in the next years. And these results will be mostly coming from people who will be smart enough to re-questioning the assumptions and putting them in light of basically the problems that we're seeing from 2030. Now, the focus I gave here has been very, I would say, of the mathematical form. I'm not saying that mathematics will be the solution. I think physics will bring also a lot of breadth of solutions. And I have many examples today where the solutions brought by people in other domain will have an impact in our domain. I think, for example, today, in the way we're tackling millimeter wave and terahertz communication, which is one of the big things for 6G. The majority of people are tackling the problem of millimeter wave and terahertz by trying to improve the signal processing that we've been doing with RF techniques and trying to bring the RF techniques to higher and higher frequencies. This is the wrong way. We know that the way to do it is to look at what optical people are doing and bring down the optical techniques to the RF ones. And why? Because by going in higher frequencies, we're approaching the optics. And it's not by going harder and harder with all these things and trying to adapt them to our things, which means that you need to spend time trying to read the transaction propagation, reading the transaction on optics and see how these techniques can be brought to your case. This is for the general trend of building these papers. And my feeling is that in the next 5 to 10 years, you will be seeing a couple of these papers happening in terms of re-questioning and building some kind of new, I would say, fundamentals. And for which basically, as usual, it will take time before we see the engineering inside. Now, you have to know that companies are investing in this, okay? And you see it today, the best research which is done in AI, unfortunately, is not done at universities. The best research which is done in AI today is done at Amazon, it's done at Facebook, in these companies. And you see it when you go in the conferences, these are the best papers which are being published. Of course, there's one reason why they are doing, in this specific case of AI, I'm taking the specific case of AI, there's a reason why they're doing much better than academia is because they have the data. You don't have the data, okay? So of course, the guys who are working in industry have a plethora of data to play with. In your case, you're just synthesizing data. And of course, this is one of the reasons the best papers are brought by them. But besides that, I think also the investments which is being done by these companies is tremendous. And even in the case that I'm taking here of Huawei, also the investment which is done on the fundamentals of ICT, I'm not talking about AI here, is also something very important. Now, the question of underdeveloped in university. So there's two aspects. There's first university versus academia, or university versus companies, and then there's the question of underdeveloped versus developed. So the first case, I think, is the problem of university versus industry. I think today, let's say the following. We saw for many years academia doing separately their research, industry doing separately their research. That was bad, okay? And then what happened is that academia decided to get closer to industry, okay? But I think the way academia got closer to industry was not the right way. What I'm saying is that in the sense that you guys are the ones which are lighting the future. You should not work on problems that industry can solve, okay? In the sense that you are the one bringing the vision. We lack vision. And so you need to work with us, and this is very important, by bringing exactly the vision and breaking the doors so that we can follow you. So you need basically to showcase the excellence that you have, but not doing the cheap work that basically we would do, but you would do it in a cheaper manner than us. And I think this is a big change that we saw in the sense that academia was very getting closer to industry, and so close at one moment that the PhD students were doing basically 3GPP simulations. It makes no sense for you guys to do 3GPP simulations. You know, we have a bunch of people doing those things. What we need from you guys is to develop the new kind of algorithms, the new ideas, and then we have the resources to do that. You should not work on the cheap aspects. You should work on the excellent aspects. So you need to go back to where you're good at, and where you're good at is to prove things. So you grave into stone that an algorithm is the best in the world. You can prove to me that the Polo code is the best thing that I can do. Second is to bring that vision, and so that we can follow, because we're lacking here what I call lighthouse keepers, people who can guide us on where to go, okay? And I think this is is happening right now, where academia has understood that in the relation with industry, but I can understand that in the past, academia felt that due to the lack of funding, then they had to accept a bad deal from, I would say, industry, in the sense that you need money, so you take the bad work and apply it. I think you need to focus still on where you are, and industry will follow, because today industry is in a situation where they need basically some breakthrough and excellence. So what you need to focus on is best paper awards, top ranked conferences, things like that, and we'll be attracted to you because you've got that ranking. Now, of course, you can do a bit of that work with industry to get a bit of experience, because of course I can understand that some of you feel connected and they need to, you know, do some stuff to learn a bit. This is okay, but it should not be your focus. It should be a small part of your work, not the majority of people just being like a branch of a company for which we will be subcontracting to you some lower work. Basically, you're paid less to do what we could do, and you're cheaper, because at the end you're harming both. You're harming the industry in the sense that basically the guys who are in the company and for which they're paid for, but they're not doing their job, and you're harming your students in the sense that also basically this is not basically in the long run where they're going to be good at. Now, so this is for my point of view of this relation between academia and industry, and we're seeing, by the way, that it's changing, and it's changing because industry is getting so far that we're back behind them. It's not good. You know, they're doing much better than us, and that's because we spend so much time just trying to subcontract. Now we need to go farther. Now, the problem of underdeveloped and developed countries is a very good thing. For sure, today, the big thing that is going to happen, I think, in the future is going to be everything which is going to be around the computing. Okay, and we see it. I mean, this is going to be the oil of the 21st century. I mean, computing resources is going to be the big thing, and for which, and by the way, the whole, I would say, geopolitical situation in the world today is mostly driven by where the big companies are creating the computing resources. So for sure, I think in your case, you have to start investing on more and more people, trying to understand better how these computing platforms are done, how you do better computing algorithms. Now, the problem you have is mostly about resources. And I think this has to go step by step. You need to start basically to work out on, I would say, more or less the algorithmic aspects, the thing of things which are cheap, you know? You don't need money. For sure, this is how you start getting momentum before you start getting a bit of investments to go up, because you need to build up your credibility. Why would I put money in your case before I start seeing some kind of excellence? So you need to look within your university one aspect where you're good at and push the people so you get the credibility by publishing in a breakthrough conference a paper. I think algorithms are a very good trend for you guys in the sense that you don't need so much resources except MATLAB, paper, and pen to start getting your credibility in terms of improving basically your status. Once you get that, you get more resources coming from company to start testing what you're doing, because you showcased a big thing in a conference, and then you start building your momentum in terms of, I would say, more resources, computing platform. But I think you need to start with things which can give you a lot of visibility first. Visibility is very important for you guys in the sense that nobody knows you. So to get visibility, you need to do some kind of good paper or some good, I would say, noise with a result that you're taking, which is not common in that sense. And I think this is where you have to focus on before spreading your resources. And even in the institute that you're involved in, Trung, this is what you need to do.
Thank you very much, Merouane. Thank you.
Yeah.
Questions from Trung? Ah. Do you have any questions?
I think there are not enough questions because I'm far away.
There are two questions here. Can you hear me? Can you hear me?
Yes, I can hear you.
One, could you explain AI and computing bring a new way to shock Shannon limit? You had a slide on that. And question two, what are the potential applications of deep learning in communication to get usability? Yeah, that's it. Yeah. What are the potential applications of deep learning in communications? Thank you.
Okay. So the first question, I'll start answering the second question. So today, the majority of deep learning in communication are mostly looked at under the angle of end-to-end optimization. I explained myself. Today, basically, if I take an end-to-end system, in general, basically, I have a channel and I have nonlinearities related to PAPR, things like that. Now, when I solve this, it's extremely complicated because I only have a linear model. So if I represent this by a black box, then basically I can do an optimization and find what is the right input so that I can target a given output. So you have some gains today when you look at the end-to-end optimization of a point-to-point link. That's the first thing. Second thing, also in the kind of receiver structure that you're building, we're seeing some gains using AI techniques where you can build up today some receiver structures which are between basically the MMSC receiver and the maximum likelihood. So in between, as you know, you have a bunch of nonlinear receivers, and it's very hard to optimize them with a very reduced complexity. So you have there also for the MIMO setting, for example, you have AI-based MIMO decoder or detectors or equalizers, which also improve the performance with respect to the MMSC and which are not at the maximum likelihood system. Now, on a more general trend, there are a lot of cases where basically we're using AI to improve the performance of systems. Let me give you a very good example. Today, we're using AI to be able to translate the kind of beam. When you know in the uplink you have a beam which comes at below 6 gigahertz, and you want to know how to beam at 28 gigahertz, for example, millimeter wave beam forming from the uplink coming at millimeter wave. Why? Because today we have FDD modes, and you know that the channel is not reciprocal. The channel is not reciprocal, so if you have an uplink channel, you don't know how to use it in the downlink. And so what we do is that we measure a lot of uplink, downlink channels at different frequencies. And next time I have a certain structure at a given uplink, I can know the structure in the downlink that I can use. We have AI-based localization, for example, fingerprinting. You know, fingerprinting is basically you have what we call a spatial signature. And when you have a spatial signature, basically you have a position, spatial signature, another position, spatial signature, another position, spatial signature. Next time you have a new position, your neural network, basically, based on the signal's signature, can tell you where it's positioned, okay? With, of course, some more sophisticated techniques than using the classical DNN, because before it was mostly a problem of classification, okay? This is how you did fingerprinting. Today, you do what we call function approximation using deep neural networks for doing AI-based localization. We have, for example, AI-based massive MIMO beamforming, which is done. You beam based on a position, you know, the beam based on a position, another beam based on a position, another beam based on a position. For a new position, you can know what is the beam you can use, because basically your neural network has learned this. So we have a lot of breadth of applications where AI basically can improve the performance. However, still said that, I don't think this is where machine learning will have the biggest impact in communication. I think the biggest impact will be about communication for improving AI. This is, I think, where we will have a big role, in the sense that you will need to build what are the right signaling formats that you need to build between the different devices which have AI capabilities, such as basically you can scale up your network. And this is, I think, where things are going to be done. Second question is about Shannon. So I told you today, AI is one part. I think the big game, revolution that we will have today, when you communicate with the TXRX, transmitter receiver, you take the channel as something independent from your transmitter and receiver. In the sense that you optimize either the transmitter or you optimize either the receiver. It's been years that we know that to improve your communication link, one way to do it is to change the environment. By the way, in a lab, that's what you do. If you do a MIMO setting and basically the channel is not rich, you will put some kind of fan in your environment so that you can have a moving scatters. This requires, of course, some physical movement of your environment to improve the link. And we know because the capacity of your environment is related to environment. These last, I would say, 5 years, we realized that we have a way to program digitally or intelligently the environment. And how you do that is by embedding your environment with some reflecting units, which are not repeater, but what we would call intelligent repeaters. They're called large intelligent surfaces that you can either program or can be auto-programmed, in the sense that they will shape your wave so that they come within a constructive interference and not destructive interference. So that it is as if I would tell you that you want to communicate towards somebody and you have a building and you ask yourself, can I move the building to improve my communication? Well, moving the building is hard. Now imagine that the building had some texture of its walls so that it could change the texture to become invisible. That would be great. Today, we have means today of doing that with what we call meta surfaces. And they are the heart today of this whole trend of research called large intelligence surfaces. And you can read a couple of my papers that I've been publishing recently on this topic about the fact that programmable environments are having a huge impact on moving the boundaries of Shannon laws. So that's the first thing. Second thing, of course, is the fact that I told you that the fact that we have memory, you change not here the notion of capacity, because capacity can only be changed with this, I would say, programmable environment. But the metric that we used to use has changed, and we have a notion of what we call semantic information, which is being built, and for which the purpose is not anymore basically about having more rate, but to be sure that I'm impactful with my goal. And therefore, when you want to, the goal is that he understands a big impact for the future in the sense that a big thing about the networks of the future will be built for machines. Let me give you roughly a big thing. 2G was mobile for phones. 3G was mobile. 5G is mobile for IoT. 6G is going to be mobile for machines. And so you need to build up some protocols where you have machines which talk to other machines. And these are going to be built on a new notion of communication called semantic communication. I don't know if there are other questions.
Can I ask a question?
Yes, please go ahead.
Yes. You touch on the topic of the academia is focusing maybe a little too much on industrial work, and I'm just curious if you have some paper that you regard as valuable with your maybe proposal, I guess, in the research today, that you would think that this is an advancement rather than maybe in industrial work.
So I don't have a paper, but I have a couple of slides that I can send you. I'm trying to have time to write a full papers providing that vision, but I can provide you a couple of slides on the different topics I've been mentioning, which is electromagnetic information theory and others. And of course, this could be useful. So what I was saying is mostly that the last years, we've been seeing a lot of papers coming from academia trying to do what industry is doing already. I mean, I don't see the point of PhD students spending time in doing a simulator which is very linked to 3GPP and trying to simulate basically the standard. I mean, this is kind of work that we're doing already in industry, and this is not where your asset is. As I told you, your asset is that you have more time to explore risky paths that we don't have time to. And so you need to take that benefit of risk that you're taking to basically increase basically the chances that you come up with some new kind of direction research instead of implementing things that we already do in our case. Now, it does not mean that you can't do it. but it should not be the mainstream of your research. I mean, a PhD student for which all his research, PhD, was done around that is nonsense. To get a bit of experience, you can, it's like an exercise, you know, it's okay. You can start to understand something, build up a simulator, do some kind of things, but that's it. And then you start focusing on something very disruptive, which are the list of theories that I showed about electromagnetic information theory, nonlinear signal processing, building tools, things like that, that will then be used by us. Now, the question of funding that was raised, I think is very important, is that you in general do that because the idea is that I will attract industry by showcasing that I can do that and they will pay me. But this is, I would say, a more short-term perspective in the sense that you will do something cheaper, but then it will not go far away. What you need to build up is rapidly some kind of credibility so that we come to you because it's things that we don't know how to do. It's not that we come to you because you do things cheaper that we could do. That is not the way things should work. We come to you not because you do cheaper, but you do it better. And this is, I think, the philosophy trend, which we're seeing a big change, which I think is also good. I don't know if I responded to your question.
Yes, thank you.
Okay.
Okay. I'm looking forward for your, I guess I want to see some examples of some research that you regard as highly valuable in terms of academic research. So,
okay.
Yeah.
Yeah, I have slides on the different subtopics that I showed. For example, in communication, if I take this example that I had about electromagnetic information theory, non-signal processing theory, multi-agent learning, I have a bunch of slides and I will send it to you. I'll send it to Trong and Trong can dispatch that.
Yes, thank you.
Any other questions? No. I think. May
I have a question?
Yeah.
Yeah. So, Merouane, do you have any example about non-von architecture for 5G or beyond application in Huawei, for example?
Yeah, so that's a good question. So the idea here totally is about what we call spatial computing, meaning reassessing the way you dispatch basically the memory and basically the cache and the data. And so we're looking at some new architecturing of basically how we connect basically the computing. And this is mostly around what we call in-memory computing. This is the big trend that we're seeing today for us. Now, there are other aspects. I cannot talk about them, but which are also important related to optical computing. This is also quite important for us in terms of research today, in the sense that many of the things that you could do, especially for AI, because one thing that you have to know is that there's the general aspect of computing, and then there's computing for AI. What I mean by that is that today you have to know that AI is pushing so much computing that we are now having computing architectures which are more focused on specific tasks, not GPU type, you know? And so what I mean by that is that we're not the only one, but many of the manufacturers are doing now what we call neural processing units, which are specifically tailored to do basically DNN. And so if you take a chipset like ours, which is sold on our phone, you would have an NPU for speech recognition, you have an NPU for image recognition, you have various NPUs. This is not a trend which is sustainable. This is why I'm saying that we need to think about things a bit differently. But the way today we're doing it because of consumption is to do some specific, I would say, units which are tailored to specific tasks. And this is what drives down the consumption, especially if you want to do basically portable computing, in the sense that you have to know that one of the big trends today is what we call on-device AI, and for which basically you need to reduce the consumption to a drastic way, okay? Mm-hmm. Now, the other aspect also that you need to know is that if you start also doing specific tasks of computing, which are on a device, you need also to revisit the way architectures like deep neural networks are done. So I take, for example, deep neural networks. They are based on a very famous algorithm, which is called stochastic gradient. So you do some kind of backpropagation. Now, when you start to do on-device AI, you need to lower down the resolutions, basically, and you need to go to something called BNN, binary neural networks, okay? And why you do that is because basically you reduce the precision to low precision AI, where the weights can only take values like 0 and 1s, okay? Now, if you oblige or constrain your weights to take only values which are 0 and 1, you cannot implement a gradient, because basically a derivative cannot be, you cannot do a derivative when you constrain it to be 0 and 1. So you need to revisit also how basically DNN algorithms are made, because basically, so a neural network or a learning algorithm by definition is optimization. Optimization is a derivative, okay? The question is how you do a derivative when you have only 0 and 1s. And so if you want to optimize when you have a 0 and 1, it becomes basically, as you all know, a combinatorial optimization. That's what we do in decoding. Decoding a decoder, that's exactly what you do. You need to optimize, and if you need to optimize with a 0 and 1, you cannot do a derivation. It's a combinatorial optimization. There, the doors are open to all the heuristics that you can imagine and how you do it. So what I'm saying is, on top also of doing some specific architectures which are related to some specific task, you also need to revisit basically the architecture based on the fact that you have constraints in terms of consumption. And so classical neural network will become a binary neural network, and for which also the kind of algorithm will change.
Okay, thank you.
Yeah.
Okay, it's been like 2.5 hours.
No problem. It was a pleasure, Tom.
Yeah. Thank you so much, Merouane. Giving a very nice talk, very various and invaluable information to us and advice. So thank you once again, and
thank you. Maybe yes, for the speaker who asked me a question, I'll send you the slides and you can forward to him. Okay.
Okay. Just one more question. What time is it in your location now?
To ask information directly either to Merouane later by email or through us here, and then we will pass on the information. Thank you, Merouane. Goodbye.
Take care.
Thank you.
Okay, thank you.